Let's have a look at an example of using Gaussian elimination to solve a system of equations for the case where the equations actually have an infinite number of solutions. And to do this, we start off with our usual process for Gaussian elimination. That is, we start by setting up an augmented matrix with the coefficients of our unknowns, x, y and z, on the left side of that matrix, then a vertical line or vertical dashed line, and then the constants on the right hand side of that line. So here our first equation is 1x plus 1y plus 1z is equal to 3. The next equation, 2x plus 4y plus 1z equals 8. And the last one, 6x plus 10y plus 4z equals 22. So this is what our augmented matrix would look like. And it also can be useful to add up the elements in each row. 1 plus 1 plus 1 plus 3 is 6 for the first one. And similarly for the other ones, we get 15 and 42, and write these row sums outside of this augmented matrix. And with Gaussian elimination, we then want to perform appropriate row operations so that all elements below the principal diagonal are 0. In other words, in this case, we want to make these three elements equal to 0. And let's start by trying to get the elements in row 2 and row 3 in the first column equal to 0. And we can do this by adding or subtracting the appropriate multiples of row 1 in each case. So the first row of this augmented matrix stays the same. The next one, though, we have a 2 here. We want to turn that into a 0. So 2 minus 2 equals 0. And hence we need to work out row 2 minus 2 times row 1. So that this first one then becomes, sure enough, 2 minus 2 times 1, which gives 0 as required. 4 minus 2 times 1 is 2. 1 minus 2 times 1 is negative 1. 8 minus 2 times 3 is 2. And the row sum of this new row is 3. And you could check that is correct by working out row 2 sum of 15 minus 2 lots of the row 1 sum, which is 15 minus 2 times 6 also gives 3, using the row sums from the previous stage. So that shows we have not made any errors here. Now for our next row, 6 minus 6 will be required to get 0, so therefore we're going to use row 3 minus 6 row 1. So 6 minus 6 times 1 is 0. 10 minus 6 times 1 is 4. 4 minus 6 times 1 is negative 2. 22 minus 6 times 3 is 4. And the updated row sum there is 6, which you could also verify is correct. Now, to get the final tableau in the required form, we now need to make this element 0. And to get this element in the second column equal to 0, we need to add or subtract an appropriate multiple of the second row. So 4 minus 4 is 0. We're clearly going to need here row 3 minus 2 row 2. So the rest of our augmented matrix is the same as before. But now doing this operation, R3 minus 2 R2, 0. Then 4 minus 2 times 2 is 0. Negative 2 minus 2 times negative 1 is 0. 4 minus 2 times 2 is 0. So you can see it's got the required form here with that triangle of zeros. So this is our final tableau. And again, you could always compute those row sums too. But looking at this final tableau, we now write out the new equations. And since our unknowns were x, y and z, our final equations are x plus y plus z equals 3, 2y minus z equals 2, and the last equation is simply 0 equals 0. Now this last equation is true but trivial, thus leaving us with 2 equations and 3 unknowns. And for that reason, because we have one more unknown than equations, one of our unknowns can take any value. Hence, we let z, for instance, be equal to t. Then, this means that the equations actually have an infinite number of solutions. And if I number those first 2 equations 1 and 2, we can now substitute z equals t into equation 2 to find 2y minus t is equal to 2, and that can then be solved, rearranged for y, to find that y is 1 plus a half t. Similarly, substituting the values for z and y into equation 1, that now gives us x plus y, which in this case we know is 1 plus a half t, plus z, which is t, equal to 3. And rearranging that, we find that in fact x is equal to 2 minus 3t divided by 2. So our answers can be written in this form, and the interpretation of these solutions is that different values of t will actually yield different points on a common line of intersection of the three planes represented by our original equations. So this is an example of using Gaussian elimination for a system of equations that have an infinite number of solutions.